So today I wanted to talk about the CRISPR-Cas9 technique that recently won a Nobel Prize. So what is CRISPR-Cas9? It's a gene editing tool, and CRISPR stands for clustered regularly interspaced short palindromic repeats. It consists of the Cas9 enzyme, which is this figure, and the gRNA, which stands for guide RNA, which pretty much gives the info on where you want to cut the nucleotides out to edit the gene. And so the way they found CRISPR was they looked at how bacteria defended themselves against viruses, and they did that by attacking their certain DNA sequences, and then keeping them in their own DNA to know, kind of like how the immune system works, to know how to attack them once they come back. So how does it work? So you have the guide RNA, and it pretty much goes around the nucleotide. It's specifically coded to find a specific sequence of nucleotides to cut out. And so the Cas9 does the cutting. It cuts out the gene that you don't want anymore. And then it either deletes it completely, where it's like cut out, and then the DNA tries to repair itself, which pretty much causes a mutation, but in the end, the gene is taken out. Or it can pretty much insert a gene, so it'll cut out the gene and then put in a gene that the RNA also carried. So how has this been used? So they have found ways to reduce symptoms in people with sickle cell anemia. And the way they do that is they cut out this gene, if you can see it, but that specific gene codes for the production, it stops the production of fetal hemoglobin. And the reason why that's not good in people with sickle cell anemia is because then they're not able to produce like healthy red blood cells. They produce the sickled red blood cells. And so researchers were like, hey, let's find a way to turn on that fetal hemoglobin so that they can produce healthy red blood cells. And it ended up working. So they deactivated and they cut out the gene that they didn't want, which stopped the fetal hemoglobin from being produced. They cut it out and using CRISPR, and then this was in the stem cells of people with sickle cell, and they were able to put in stem cells that they genetically engineered without that gene that stops the fetal hemoglobin. And so the people with sickle cell were able to produce healthy fetal hemoglobin cells. So where could this be used in the future? So this could be used to like correct any sort of, well, not any, but many sorts of like inherited genetic disorders. So genetic blindness, muscular dystrophy, cystic fibrosis, cancer, and HIV. And so it's a really new technique. It's said to be the easiest and most inexpensive compared to like previous techniques. But the reason it hasn't been used a lot is because it's fairly new, so there's not a lot of research into like long-term effects and everything. And in the end, the patients have to go through chemotherapy to re-implant the stem cells into their bone marrow, which costs a lot of money. So that's pretty much why, but pretty interesting technique.